Welcome to today's class. In our topic today, we'll be talking about diode DC characteristics. Under this topic, we'll be looking at the IV characteristics of the ID diode and that of the practical diode. So let's begin with the ID diode. Now, what is an ID diode? An ID diode is a diode that offers zero resistance and zero voltage drop in the forward direction. So it offers zero resistance to the flow of current. If you think about the Ohm's law, for example, we have Ohm's law is equal to V equal to IR. Now, I will be equal to V all over R, which is the resistance. And if we say that the resistance is zero, so that simply means that the current will be infinite. So for an ID diode, the current is infinite. The ID diode is similar to the ID diode in the forward direction is similar to a switch. Now, shown below is the circuit of an ID diode. Shown below is the circuit of an ID diode in the forward direction. Now, this is similar to a switch that is closed. A switch is used to make or break a circuit. Now, let us look at the similarities between the ID diode in the forward direction and that of a closed switch. So we see, because the switch is closed, current ID will flow through the circuit. So, and there is no voltage drop across the diode. Voltage drop is zero. So in this instance, the diode is on and the current ID is infinite. So the ID diode behaves as a short circuit in the forward direction, allowing current to flow through the circuit. So that is for the ID diode in the forward direction. What about in the reverse direction? What about in the reverse direction? Now let us look at the operation of the ID diode in the reverse direction. Now, for the ID diode in the reverse direction, it is an ID diode offers infinite resistance in the reverse direction. Infinite resistance in the reverse direction. Remember, I is equal to V over R, and if the resistance is infinite, then simply means that the current is zero. So no current flows through the ID diode in the reverse direction. Shown below is the circuit of the ID diode in the reverse direction. So shown below is the circuit of the ID diode in the reverse direction. Now, this is similar to a switch that is open, as you can see here in this circuit, a switch that is open. So because the switch is opened, no current flows through. So in this case, it is an open circuit. So an ID diode behaves as an open circuit in the reverse direction. Now, let us look at the IV characteristics of diode. Now, the ID diodes in the forward direction, we said that the current is infinite, the diode is on, but in the reverse direction, the current is zero and the diode is off. And let's plot the IV characteristics of the ID diode. So we said that in the forward direction, the diode is on and it acts as a short circuit. So the entire current flows through, infinite current. So the plot is going to look like this for the ID diode in the forward direction. While in the reverse direction, the diode is off and no current flows through. So that's the IV characteristics of the ID diodes. So now let's look at the practical diodes. Now, why there are no voltage drop across an ID diode there is a finite voltage drop across a practical diode. In the forward direction, the diode offers a barrier to the flow of current. For silicon diode, it is 0.7 volts, while for germanium, it is 0.3 volts. And so the IV characteristics of the practical diode is going to look something like this. Let's try to plot the IV characteristics now of the practical diode. Now, because of the barrier that is offered to the flow of current, we're going to have in the forward direction, you have it overcome the barrier. Say for instance, if it is silicon, that will be 0.7 volts, about 0.7 volt. And as soon as it is able to overcome the barrier to the flow of current, which is 0.7 volt, you see a significant rise in the current in the forward direction. Then while in the reverse direction, this is actually a compressed K. In the reverse direction, you see the current flow in this direction, and then gets to the breakdown voltage, and then you see a sharp increase in current in the reverse direction. So that is the IV characteristics. You have the forward bias region, this is the reverse bias region, while this is the breakdown region. Right, so we have three regions: the forward bias region, the reverse bias region, and the breakdown region. Now in the forward bias region, we have that VD is greater than 0, as you can see. In the reverse bias region, we have that VD is less than 0. Why? In the breakdown region, we have that V is less than minus. Okay, in the breakdown region, this is the breakdown voltage, VBK. So in the breakdown region, we have that V is less than minus the breakdown voltage of a practical diode. Now for the forward region, the current flow is given as ID is equal to IS exponential VD all over eta V theta minus 1. This equation is also referred to as the Shockley equation or diode equation, where IS is the reverse saturation current and VD is the forward bias voltage, VT is the thermal voltage, and eta is the ideality factor. In most cases, it is equal to 1. And V thermal is also equal to KT all over Q, where K is the Boltzmann constant, giving us 1.38 times 10 raised to the power minus 23 joule per Kelvin. And then you have Q is the charge on the electron, which is giving us 1.6 times 10 raised to the power minus 19 coulomb. And then you have temperature T in Kelvin. At room temperature, V thermal is giving us 25.3 millivolts, and that's approximately equal to 25 millivolts. So if V thermal is not given and you are told that it is at room temperature, you can either use 25.3 millivolts in your calculations or 25 millivolts. So we've just seen the IV characteristics of the ID diode and that of the practical diode. So as a way of review, we've talked about the ID diode. I would say the ID diode is a diode that offers zero resistance and zero voltage drop in the forward direction, and thus the current is infinite. It is similar to a switch which makes or break a circuit. So in the forward direction, it is short-circuited, the diode is on, and current flows. In the reverse direction, it offers an infinite resistance to the flow of current, and so the current is 0, it is similar to a switch that is open, and so it is open circuited. And that is the IV characteristics of the ID diode. You see a straight line in the I direction, the positive direction, and a straight line in the VD direction in the negative axis. So that's the IV characteristics of the ID diode. And then we went further to talk about the practical diode, and we say for the practical diode, it's in the forward direction. The diode offers a barrier to the flow of current, and the current must be able to overcome this barrier before the current flows. And so we just saw the IV characteristics of the practical diode, different from that of the ID diode. So we have three regions. We have the forward region, and then you have the reverse region, and the breakdown region. So that's a sketch of the IV characteristics of the practical diode. And then we looked at the diode equation. ID is equal to IS exponential VD over eta V theta minus 1, and where V theta is equal to KT all over Q. And this will be able to assist us in calculating for the current that flows through the diode. So that is all for this class. See you in our next class.